Good afternoon, everybody. Welcome to sunny afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hi. Hope you all had a good time since we last met. I went to one of the more dangerous places in the world for me, and that's Costco. Because usually if I can get out of there under $400, I've done good. I only go there about 4 or 5 times a year and stock up on basics and other things. But one of the things I got last year when it was on sale, I only got a couple, and I went there. It's still on sale, I think. I don't know. These tops, and these tops are really nice and warm. See how they're fleece lined, and they got pockets, a nice zipper, and they're only $14.95 a piece. So I got a few more, so I got stocked up on them, and I really like them. They're nice and warm. I keep my house on the little cool side because I'd rather spend less on heating and put on a top than not have a top on, spend more on heating. All right, couple important things, important announcement. One, Wednesday we will have class. I'll say that again. Wednesday we will have class. If you can't make it, guess what? You can watch the video later on afterward, and we'll have our lab. ECC, wrong school. I was going to do the wrong school. ECC, Algae Community College, on Wednesday before Thanksgiving. This Wednesday officially closes at 5 p.m. Therefore, I can't have my office hour because we're closed, and therefore I won't. But if you need help, let me know. We'll find some time to do it. Now, a couple other things. Let me remind you that this Wednesday, I will go through the fats and oils problem set. Keep up. Also, we'll do the lab this Wednesday. And let me remind you about the extra credit project. It's in the assignment area of D2L, and it's 10 points. I would highly recommend you don't wait until a day or two before. Do it, and then email me a copy of your project, your table, and I'll check it. If there's anything wrong, I'll let you know and help you fix it. That way, anybody who tries it, there's no reason why you shouldn't be able to get 10 bonus points. And I'm looking around, and last week when I saw an example would be Carmex, phenol, and when there's more than one functional group in a molecule, you only have to name one, not all of them. And that would be either a benzene ring or aromatic. Either one works for me. I'm the one gradient, so I know it works, or alcohol. Now, one common mistake about the extra credit project is, oh, I've got 10 molecules I have to get, up to 3 from any product. So that means you got to look at 4 different products. They all have to be different functional groups. No, they can all be ketones, alcohols, whatever, or any combination. They just have to be one, an ingredient that's actually on an ingredient list of something you could buy. And 2, they have to include a functional group that we talked about in our class. The reason I do that second is students look at names and they just get it wrong all the time. And so that way, if you look at a isocyanate or a, what would be another one, isocyanate, students get that wrong. So that's the extra credit. And good news, I found my models. I couldn't find them and I was getting upset. And over the weekend, I did some serious searching and found them. Now, let's get to work. Now, we already covered this. Everybody see chiral center? Thank you, Christiana. All right, now, if I assume E is red and C is yellow, E is red, C is yellow, something I didn't have a chance to do last week. Here's the molecule, and it's in 3 dimensions. This is loose for whatever reason. And here is its mirror image. And notice silver on top, black back, and my red wants to not stay in place. And these are mirror images. If I go like this, the blacks line up, the silver, but if you notice, the red and yellow don't. And if I line up the red and yellow, now the black and silver don't line up. So these are, I just dropped the piece. I'll have to find it in a second. Give me a second, actually more than a second. I'm back. And so these are mirror images, but they're non-superimposable. So one, they're enantiomers. Remember, molecules that are non-superimposable mirror images are enantiomers. And this would be a chiral molecule. Same thing with this one, because it has a non-superimposable mirror image. And I wanted to show you that, and I did. Now, last Wednesday, I believe I started talking about enantiomers. Yeah, I did that. And enantiomers are non-superimposable mirror images of each other. And we did this, but if I were to ask you, my desk is full with all the models and everything. If I were to ask you, draw the enantiomer of A, what would you do? Hint, mirror image. Your turn. Draw the enantiomer of that molecule. And when you're done, give me a thumbs up. Thank you, Christiana. Thank you, Andrew. All right. Now, you don't have to, but I like to put in my mirror, and good habits I don't change. Isn't that amazing? It's worked all my life. So we have these 3 carbons. This is a Fisher projection. I'll talk more about it when we're through with this. And then this is an aldehyde. Remember, and because you have a double bond to this carbon, it's not chiral, so I don't have to worry about writing a mirror image. This carbon at the bottom has two hydrogens, so it can't be a chiral carbon, so I don't have to worry about it. If you wanted to, you could, but I don't. Organic chemists are lazy. And now let's look at this carbon, what's close to the mirror, hydroxyl group. That's what we'll see. What's farthest away, hydrogen. Next carbon, what's close to the mirror, hydrogen. What's farthest away, hydroxyl group. And the final carbon in this molecule, as a chiral, is this one. And so this would be the enantiomer. And you can't pick it up and rotate it to see if it's superimposable. When you have a Fisher projection, which is what these are, you can only just pick it up and lay it on top of each other. So, and we did some last Wednesday, so I just wanted to bring you up to speed, and you are. I talked about the diastereomers, just to make you aware, those are stereoisomers also, whose molecules are not mirror image, and cis and trans molecules are diastereomers. All right, now, click, switch, will this be on test? No, but I still want to show you. If you have a three-dimensional molecule like this, and you're looking at it, let's see, and if you rotate it toward me, C is yellow, E is red. When I look at it, and if I were to flatten this out, which I'm not because I'll break the model, you would come up with something like this. And this tells you E and C are coming toward you, just like this is coming toward you. And notice A, the black rod, and D, the silver rod, are going back away from you. And this is a Fisher projection. These are coming toward E and C, and A and D are going back. And these show three dimensions in a two-dimensional way. And these were figured out by one of the great organic chemists, a German organic chemist, Emil Fischer. Let's see something. All right, here's Dr. Fischer, and he's known for Fischer esterification, but what he's really known for is his work in sugars. And he did a lot of other things too. And he came up with the Fischer projection, and he did a lot of research with aldehydes and ketones, which really we're talking about sugars. And he elucidated, that's a fancy way of saying he figured out how to the structures of various sugars and carbohydrates. And he did that by making various what's called derivatives using phenylhydrazine. I think later on 2,4-dinitrophenylhydrazine. I didn't know this. He discovered barbiturates and a whole lot of other stuff. Wow. Anyways, for his work, he won the Nobel Prize in, I think, 1904, give or take a year or two. 1902. I was close. All right. Let's get back to our slide. So this is a Fischer projection, and we use it all the time. Now, let's look at the following molecule and think about chirality of the monosaccharides. And we show this by using, again, switch is still off, the DL designation for right or left of the highest chiral carbon. And that would be in this compound, this one. This is carbon 1, 2, 3, 4, 5, 6, but only these are chiral. And the highest chiral carbon, and again, switches off, but you may see this in your other classes, which is why I want to teach you this. If the hydroxyl group is on the right, it's called D, and this is glucose. If it was on the left, it would be called L. I believe D and L are short for the Latin for right and left, dextrose and levatory. That's about the extent of my Latin knowledge. I know other languages, but not Latin. Not that there's anything wrong with it, but that's something that just never came up in my education. That's not what I wanted. I'll accept all cookies. This is it's called Millipore Sigma or Sigma Aldrich. And it used to be Aldrich Chemical Company till Sigma bought them out about a decade ago. And this is probably the finest company in the world to buy small quantities of chemicals. And small quantities, I mean under a pound or two. If you're going to buy a couple 100,000 pounds, you don't go to Aldrich. But if you need a small amount, you do. And notice they have a product called dextrose, which is really D-glucose. And the D tells you the hydroxyl group is on the right. Now they show here the cyclic form, which I'll talk about. And that was nice. I got to see their bottles. That's not what I was looking for. So that D tells you it's on the right, the hydroxyl group of the highest chiral carbon. Now, interesting story. When I taught this, one of the students I had in Chem 170, she was going back to get her master's degree in nursing and said, oh, that's why there's a D on the D-glucose in the bottle solutions we use for intravenous feeding. And I said, yeah, that tells you we're the hydroxyl group. And I learned something new too, that's what they use for intravenous feeding of patients. You learn a lot, and I always learn a lot from my students. Never, ever give up learning. I haven't. All right, now, switch is still off. There are certain key physical properties when we talk about enantiomers. And they're identical enantiomers, which is non-superimposable mirror image, like your hands are enantiomers, but they're not molecules. They're identical, all their physical properties like melting point and other things, except for two things: optical activity and reactivity with other chiral molecules. And this is to get what's called stereoactive or optically active, molecule. And guess who was the first one who isolated stereooptical active molecule? Some guy who's got the name of Louis Pasteur. Why does that sound familiar? Because you know him for pasteurization, how he came up with Here's a picture of them. See how our organic chemists have beards? Anyways, French chemist, actually microbiologist and chemist, and he's known for pasteurization, a lot of other things. But one of the most important things is molecular. And what he did, and this must have been very tedious work, he separated the mirror image crystals of tartaric acid. And tartaric acid has this structure. It's sort of like a sugar, but it's not, and it's got chiral carbons. And with tweezers, he painstakingly separated the crystals. Amazing. Now, what's the optical activity? Optical activity is a compound that rotates plane polarized light. Remember, switches off, click. What's plane polarized light? Well, if you're outside in the sun or in my office, I don't know if with my reflecting forehead, but anyways, the light coming down comes in waves. And the waves are not just like this. I like these special effects. They're all degrees of the compass, 360. Now, if you have what's called a polarizing film, you can block all but one wave. So only this is coming at you. How many of you are familiar with polarized sunglasses? No one. Okay. Well, those are sunglasses. I see one person that block out a lot of sun. They're really good. And how do they do that? They stop all but one or two of the waves coming to your eyes. So that cuts down the intensity, the brightness of the light coming to your eyes. Why they make good sunglasses. Well, it turns out if you take a plane polarized light, one wave, one angle, and put it through a solution, assume this is not just water, and it's got chiral molecule, optically active molecule in there, it rotates it either to the right or left. And depending on the purity, assuming it's 100% pure in a solvent like water, which is not optically active, at a certain temperature, it will always rotate at that degrees, right or left. And that's used as indication of optical purity or how pure the molecule is in terms of other isomers. By the way, and I'll never ask this on a test, when you have a mixture of different isomers of the same molecule, that's called a racemic mixture. And helps if you see what I'm looking at. All right, everybody see types of optically active compounds on your screen. Thank you, Christiana. All right. Thank you, Andrew. Now, here, and again, switches off, but you'll see if it rotates plane polarized light to the right, it's given a plus symbol in the front of its name. And if it rotates it to the left, it's given a minus. And if you remember, the Aldrich said D plus glucose. Now, there's no way any chemist can look at a structure of a molecule and say which way it rotates plane polarized light. You have to go in the lab and measure it. All right, back to chapter 16, classification of monosaccharides. I'm going to turn the switch off right now, but this is for other classes you might have in the future, which is important to know about. And here we have what's called aldoses. And don't forget, I've never been a carbohydrate chemist. I've worked in many areas, and I did a couple experiments long ago with this, but I'm not really a carbohydrate chemist, but I do know my carbs. Oh, do I know my carbs? But anyways, this is an aldose. Why? It's a monosaccharide polyhydroxyl ketone or aldehyde. In this case, it's an aldehyde. Remember, my software and carbohydrate chemist write an aldehyde this way. So aldose or aldoses are monosaccharides that contain an aldehyde, and that's this. And this is glucose. Actually, it's D plus glucose, but I'm not going to put that down. Now, there's something called ketoses, and those are monosaccharides that contain a ketone, carbonyl with two R groups that can be the same or different. And here we have our carbonyl group. This is R, and this part I'll call R prime. And this is a monosaccharide. How many of you have ever heard of ketosis? I see one person, and that's a significant, how should I say this, medical problem with diabetics. Thank you, Andrew, and you did. Quick story. How long ago was it now? I think it was 4 summers ago. I was teaching Chem 170 in the summer, and I saw 2 students had something on their arm. That's unusual. And in the lab, I said, whatever that is, can you take that off? No, that's my glucose monitor. And both of them were diabetics. I said, be careful in the lab. Don't get anything on there or anything. They thanked me for my concern. And I also asked them in private, if you have any medical problems, how do you want me to handle it? Which they told me. And I also asked them, and I asked students when we're doing face-to-face, if you have any medical problems, see me in private. And what I'd like to know is, if you do have a medical incident, how do you want me to handle it? The other thing I would ask you to do in either your wallet, purse, or backpack, have a card with a phone number of someone I should contact if there's a problem. And I've had diabetics, I've had people who have epilepsy. Luckily, I never had an epileptic seizure, but I had students who had medical difficulties, and I knew how to handle it because they told me. And ketosis is one of those that diabetics have to be concerned about. And that's because you have low carbohydrates in your blood because of low glucose. And that provides, when it's normal, ketones, which I don't know how they do it, which is energy for your brain and can be very serious. But anyways, this is a whole area I really haven't worked in because I'm not a biochemist. All right, now, a couple things you should know. Click, switch is on. What is a sugar? I'm sure you've been in a restaurant, somebody says, could you pass the sugar? And a sugar is what we call mono or disaccharide. So you should know a sugar is a mono or disaccharide. Now, for now, I'm going to turn the switch off, but I'm going to turn it on a little while. Here's D-glucose. D-glucose, and we'll learn later in the chapter, it's the most abundant. Why? It's the most abundant sugar in nature. It's the sugar in our blood that obviously provides energy to different things. And it's called an aldose hexose because it's got an aldehyde and hex 6 carbons. And it rotates plain polarized light to the right. And here's the structure. Remember, you don't have to memorize the structure. Now, in a little while after I go through something else, I'll explain why there's this equilibrium to the structure on the right for D-glucose. Now, this is a structure for D-fructose, and it's a ketohexose, 6 carbons, ketone. This is the sweetest sugar of all sugars available. And it rotates plain polarized light to the left. And it's found in high fructose corn syrup, which is why high fructose corn syrup tastes, that's sweet. Let's try something while I have the time. I can spell it right. Everybody see on their screen? I don't know if this is how accurate this is, but if you look at glucose, which is, if you think sucrose table sugar is 1, glucose is not as sweet. Now, fructose is this range, but in the higher end, it's almost twice as sweet as sucrose, which explains also it's a lot cheaper to make once organic chemists help biochemists or farmers make high fructose corn syrup. And if you look at a lot of things you can purchase, like pop, you'll see, and ketchup and other things that are highly sweet, they contain high fructose corn syrup. About 30, 40 years ago, before organic chemists figured out how to help make high fructose corn syrup, if you looked at a can of pop or ketchup, it would have sucrose in there. Now it's high fructose corn syrup because it's the sweetest sugar around. And it forms this cyclic form, which I'll talk about in a little while. Now, what this is right here, and this ring right here on the right, those are called Hawthorne projections. And they show stereochemistry in 3 dimensions. And Dr. Hawthorne came up with the idea. And so we have it using 2-dimensional structure, like on a piece of paper, to specify 3-dimensional structure of a cyclic form of a monosaccharide. It won't be on the test. Years ago, I tried teaching it, and I put it on the test 2 classes in a row, and every student got it wrong. Every. And I realized, one, this is hard to get. Even for me, it's hard to wrap my head around it at times. I do, but it wasn't easy to master it. And I've got a PhD in organic chemistry. So I no longer include it on the test. Thank you, Dr. White. You're welcome. Now, let's talk about the hemiacetal and hemiketal form of glucose and fructose. Now, from test 2, you learned the following reaction. You take a ketone or aldehyde when R prime is hydrogen, it's an aldehyde. When it's carbons, it's a ketone. Reacted with an alcohol and acid catalyst. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . you form this compound, a hemiacetal or hemiketal. This attacks the carbonyl carbon and forms this new bond. Now, this is called an intermolecular reaction. And there are two types of reactions. One is intermolecular, to separate, and the other is intra, all in one molecule. Oh, that's a different one. I'll never use that. All right. If you had to go to one of my favorite places, Amsterdam, which is in the Netherlands, how favorite? I keep this around. Everybody see that? Well, let me make it right side up. Focus. And this is a 2.5 guilder coin. Now that for many years, Netherlands, like other countries in Europe, are on the euro, they don't use this anymore, but I still have one. And because I went to the Netherlands a lot. And if you had to fly from the Chicagoland area to Amsterdam in the Netherlands, that's a country outside the US, and you go to the international terminal at O'Hare. Take KLM, that's the amazing airline, probably one of the best I've ever flown in my life. I've been on a number of them. Makes American Airlines that bad. And KLM is that good. Well, it also helped. I was always flying business or first class. That helped a lot. But on an 8-hour flight, that was nice. But anyways, if we were going from Chicago to New York, that's in our country. So we wouldn't have to go to the international terminal. We'd go to a regular terminal because it's intra-country. And the same thing is true about molecules. Now, let's look at the following. But first, I want to be subtle. Everybody get the message? Hint, know this. What do we need to know? Two days later, I'll be finished writing this. No. All right, this is glucose. And if you notice in this molecule, we have an aldehyde and we have an alcohol right here. And it can undergo this reaction in the same molecule. And when it's intramolecular in the same molecule, you don't always need a catalyst. So what happens? Just like here, this alcohol attacks the carbonyl. This alcohol, and it's always, this is C5, 1, 2, 3, 4, 5. This alcohol attacks that carbonyl. Now, because you don't have a catalyst and it's in the same molecule, it's in equilibrium with this. Now, instead of having you draw the Hawthorne projection, I came up with an idea how to help students out, and it works. It helps students. Whatever is not involved in the reaction won't change. Okay, now this oxygen here is this oxygen here, which becomes this oxygen here, bonds to that carbon, which was the carbonyl. this one. So I'm going to show you the world's longest and ugliest carbon-oxygen bond that makes your life easier. This is now bonded to that carbon, which is like that. It will still have the hydrogen on there, and like up here, it will now have a hydroxyl group. And you should know how to do this. If I give you glucose and double-headed arrow, give the product, you should be able to do this. If I give you the cyclic form of glucose, double-headed arrow, what's the starting material? You should know how to do glucose, or if I get nice on test 4, write the name. Either way works for me. If this didn't happen, this is the first step Mother Nature uses to make all the carbohydrates, complex starches in our life. If this didn't happen, well, we wouldn't have sucrose, table sugar. We wouldn't have wheat, rice, or potatoes, or all the good things in life like French fries, pizza, Lay's potato chips, the sour cream and onion oil. Those are good. And this is important. You should know this. Again, what happens? This hydroxyl group, alcohol, is this alcohol. It attacks the carbonyl right here. And it forms this bond here is really this bond. And this, what was the carbonyl, has a hydroxyl group on it, and R prime was a hydrogen. That's still on it. And everything else is the same. And like I said, you should know this. Let's go through this again. This hydroxyl group alcohol attacks the carbonyl carbon of the halide to form this hemiacetal, which is essentially this reaction, but in the same molecule. R and R prime are connected together. That's the only difference. Or not R prime, R double prime. And that's how you get that ring. Now, if I look at the clock, I'm going to have to take let's take a break now, because otherwise I'd have to rush through the next part, which I don't want to do. Let's take a 5-minute break, come back at 1:50, and we'll continue on the sweet stuff. We're dealing with sugars. See you in 5. Let me do that again. That's better. I'm back. All right. Welcome back. Let's continue where we left off. Now, I was showing you how you can form the cyclic form of glucose. And if you see on your screen the Hawthorne structure, everybody see that on the right here? Thank you, both of you. Well, which is easier for you to understand, this or this? And I would think my way is easier. Well, I know that from students' experience in the past. All right, now, this is glucose. Again, no new reaction, except it's happening in the same molecule. Aldehyde or ketone, alcohol, because it's in the same molecule, you do not need the acid catalyst. And you form a hemiacetal or hemiketal. And this is for glucose. And same reaction, if it looks like deja vu all over again, it is. This attacks the carbonyl carbon. What's attached to that is still attached. This opens up the hydroxyl group, NOR. And when R prime is alkyl, you form the hemiketal. When it's hydrogen aldehyde, the hemiacetal. Now let's look at the structure of fructose. Let's see if I can draw it nicely. Now I'm going to cheat by putting a C here. Normally you just have two lines from the oxygen right to the line coming down. And here we have fructose, which is the sweetest sugar in all of nature. And here I have a carbonyl, carbons here, and here it's a ketone. But at C5, carbon number 5, I have this alcohol. And because it's an intramolecular reaction, I can go technicolor on you, this hydroxyl group, whoops, went too far. This hydroxyl group attacks the carbonyl carbon, just like this one attacks the carbonyl carbon. Now, whatever is not involved in the reaction, I can rewrite. So I will, because this comes along for the ride. Now, this hydroxyl group of the alcohol, this oxygen here is this oxygen here bonded to the carbon that was the carbonyl carbon. So instead of doing a Hawthorne projection, I came up with the idea similar. The world's, let me clean this up. The world's longest carbon-oxygen single bond. And notice on this carbon, there's a hydroxyl group. So I'll put that in. And I forgot to be subtle. Get the hint? Know this. And you should know if I put the structure of fructose and have an equilibrium, you should be able to draw its hemiketal form over here. If I do the hemiketal form in the equilibrium, you should be able to draw the structure of fructose. Or if you remember, you can put the name down too. I sometimes get nice on test 4. Which reminds me, time for a public service announcement from your host, me, Dr. White. I don't know why it happens, but I've seen it often enough that I'm making this public service announcement. Test 4 should be easy, and for a lot of students it is, but some just do awful. I mean, why? I don't know. I've guessed that, well, it's the end of the semester. This stuff doesn't look that hard. I know these reactions, so I don't have to study hard, and it shows. This is a 100-point test with 5 bonus points. And you should always try, at least I always did, every test, get as many points as possible, which means study hard. Please, because I see students, they've been getting 90s or better on tests, and then test 4, they don't study as hard and they get a 75. That doesn't help your grade. So be sure to do the practice problems and study for test 4. And I should mention, and I'll probably sometime Thursday, no, not Thursday, but Friday, if not, maybe even Wednesday morning, I'll put out the information on test 4. Test 4 will be a week from this coming Wednesday. Let me look at a calendar. It'll be the 30th of November. It's in the syllabus, but I decided to tell you November 30th will be test 4. Wednesday, we'll go through the fats and oils problem set. We'll finish up on Wednesday, if not today. Today, I might even finish up this carbohydrate chapter. I haven't told you this, but I've been stealing time from you. When we normally face-to-face, I teach at ECC. On Wednesdays, I only have 50 minutes for lecture, and it's right to the lab. Since we've been doing lab online, I've been able to spend more time on Wednesday on lecture too, which means more practice problems for you. Shh, don't tell anybody. Shh. So if I end a little early, you've been getting all your time this semester, actually a lot more. All right. So much for my public service announcement. Let's get back to here. Let's go through this again. You have an aldehyde or ketone reacted with an alcohol and acid catalyst. You form a hemiketal or hemiacetal. In the case of fructose, you have a ketone. You have at C5, this carbon right here, an alcohol. And the red line, just like on above, you have a tack of the hydroxyl group. Organic chemists are violent. And it forms this hemiketal. This oxygen is this oxygen. This carbon is this carbon. And this bond is this long bond right here. And if I give you fructose and a double-headed arrow, 3 points, give the product or products of the following, you should know how to write this. And if I give you this hemiketal, you should know how to go backwards if I had to fructose. And you should know this. So you should know this reaction with glucose And the same one, but obviously a different product, with fructose. And which is easier to write? The Hawthorne projection, and its official name is beta-D-fructofuranose. Again, I'm not a sugar chemist, so. But anyways, it's easier to draw this structure when you start with this, or this structure when you start with fructose. How many think the second one is easier? Give me a thumbs up. Thank you, Christiana. Thank you, Andrew, which is why I invented it. And now when I put this reaction on test, if I did, anyways, students don't get it all wrong, thank goodness. All right, let's move on. We did Hawthorne projection. We did the hemiacetal hemike reduction seaboard. Oh, a long, long, long time ago. Test number 2. You have a catalyst, and it's equal to nickel, platinum, or palladium. Remember, carbonyl, carbon double bond oxygen, has 1 pi bond and 1 sigma bond. And in ketones and aldehydes, that pi bond, you can break real easy. And what happens in hydrogenation? Each atom of the double bond gets a hydrogen, and you make an alcohol. So ketone or aldehyde, hydrogenic catalyst, this is called hydrogenation. You make an alcohol. Hold on. Let me get my pad better situated. That's better. And your turn. What would be the product or product of the following reaction? But I will tell you, alcohols do not react with hydrogen and nickel catalysts. Alcohols do not react with nickel and hydrogen or hydrogenate. And I will give you one more hint. 3 lines means identical or equal to this. So your turn. What's the product or products, organic product or products from that reaction? By the way, that's glucose. Thank you, Andrew. Thank you, Christiana. My turn. And if we look at this, this is an aldehyde. And what happens? What's the general reaction? Aldehyde or ketone, hydrogen, and a catalyst that's equal to either nickel, platinum, or palladium. You break the pi bond, and each atom of the double bond, the carbonyl, gets a hydrogen. You make an alcohol. Everything else comes along for the ride. Well, in this case, you're not going to break any carbon-carbon single bonds, so this is all going to be true, unchanged. And this, which is this, will become this alcohol, which I can write this way, or I could have written like this, and the rest is the same. Now, one of the questions, I haven't done this in a while, and I should have, but I'll do now is, why am I learning this stuff? Well, the obvious answer is someone told you had to take Chem 170, a one semester organic, to get into a school or a program like nursing or others, health related, and you need to take it. Why learn this stuff? Well, let's look at the reaction we just did. Now, this is fructose. I'm sorry. I got it wrong. This is glucose. This molecule has a common name. I don't know how it got its name, sorbitol. And so what, you're probably asking, which is a good thing. Always good to question things. Does everybody see on the screen there sorbitol? And here, every bend in a line is a carbon. They show stereochemistry instead of Fischer projection. You have 1, 2, 3, 4, 5, 6 carbons. Each one has a hydroxyl group on it. And if we go back to what I just showed you, you have 6 carbons in sorbitol I have here, and each one has a hydroxyl group. This is showing it with Fischer projection instead of what's called three-dimensional or the dash wedge projection, which I know, but I don't teach in this class. And that's what these dashes and wedges show you. All right, now what is sorbitol? Well, it's from the reduction of glucose, which I just showed you. And it makes an aldehyde into a primary alcohol. And what is it used for? Well, it's commonly obtained from the reduction of glucose. Take glucose, like I just showed you, hydrogen and catalyst, and you'll get sorbitol. And one of its main uses is as a sweetener. And if you look at, it's not as bad for people as sucrose or fructose, and it's found often in diet foods, and a big place is cough syrups. If you look at your cough syrup, if you have some over-the-counter cough syrup, you will find it probably has sorbitol in it to make it sweet. So when you or someone young takes it, no, it's sweet. Oh, that's not too bad. And that's sorbitol. Do I have time? I do. Now, everybody see out here, terpen, which is terpen hydrate with coating. Quick Dr. White story, because I got time today. We're ahead of schedule. Back when I was about 10, I came down with asthmatic bronchitis. Not a fun time. That whole summer, I had to stay indoors, and most of the time, I was trying to cough my lungs out. It was awful. Luckily, my father was a pharmacist. At that time, the chain pharmacies were almost non-existent or very tiny. Like Walgreens was really tiny. And most of the pharmacies in Chicagoland were independently owned. Like my father had a store. And what did he do? Well, he had back then, they didn't have packaged products like you go now to a pharmacy, even if they have a prescription, a lot of it's already been packaged in a bottle for you. Back then, pharmacists would get big bottles, like gallon bottles and stuff. And if you needed something that was liquid, they'd have a supply of empty bottles, different sizes, and they'd fill it, put a label on it and everything to fill your prescription. Well, since my father owned a place, he brought back a big quart bottle of elixir terpen hydrate with coating. And essentially all that was, in reality, 90 proof alcohol with coating, which is a very strong painkiller and it has nice effects on your brain. And I take about every morning or more than that, a couple tablespoons of this, and I'd feel better. And I also stopped coughing. Well, just think of this, a 10-year-old doing a couple of shots of alcohol with codeine. You'd feel well. Well, after I got well, one morning at breakfast, right before I started breakfast, Father was sitting at the breakfast table. I went over to the big bottle and I went and got my couple of tablespoons of elixir terpen hydrate with codeine. And my father said, you're over your asthmatic bronchitis. You don't need that anymore. I said, Dad, that makes me feel good. And he laughed and said, yeah, I bet it was. Sure, you're going to school right before school, do a couple of shots of vodka with codeine in it. You'd feel good too. And I did. And shucks, he took that bottle back to the pharmacy and no more. But for a number of years, you could get that over the counter. At one point, you had to sign for it, and they stopped selling it because people were abusing it big time. And that's my personal story. All right, let's talk about glucose formation from monosaccharides. And don't write anything down from this slide. Glucoside is the acetal or ketal form of a cyclic monosaccharide, and glucoside is the glycoside from glucose. And a note from Dr. White to Dr. White, remember the reaction of methanol. Ooh, okay, I will. All right, now, I told you earlier, no new reactions. Well, I sort of stretched the truth a little by doing the following. And by the way, click switches on. Better yet, if I could turn a dial that only went to 10, I've just turned it to 20. I stole that from the movie. This is Spinal Tap. But anyways, oops, wrong color. A long time ago, test number 2 material, you learn if you took a aldehyde or ketone and now 2 molecules or moles of an alcohol and acid catalyst, you will form the ketal or acetal. Now, what I didn't show you is the following. This you learned before. Now the hydroketone plus one molecule of an alcohol and acid catalyst will form the hemiacetal hemiketal. And now the second alcohol converts this to this. What I didn't show you was the second alcohol doesn't have to be the same as the first. If you have this molecule, and this is a new wrinkle, and it's the only new thing I'll be teaching the rest of the semester in terms of reactions. If you take a different alcohol and react it with a hemiacetal or hemiketal, you'll form this new acetal or ketal. Now, this is symmetrical because both R groups on the oxygen are the same. Let's try this arrow again. This is unsymmetrical. On the oxygens, the R and R triple prime can be different. And that's why we call it unsymmetrical. And this new step right here, Mother Nature uses. Did I tell you Mother Nature is the greatest of all organic chemists in my mind? And a lot of other people, I would hope, too. Things she does is amazing. And the second reaction allows Mother Nature to make all the starches we know and enjoy in our daily life. So let's take a look at this. Again, I better be subtle. Can't know this. Everybody get the message? So let's look at, and again, let's consider this the last part of this. If I take a hemiacetal or hemiketal and react it with a different alcohol, I'll replace this hydroxyl group. Remember, everything attached to that carbon except the hydroxyl group will still come along for the ride. And replace it with OR triple prime. We were in a classroom, you'd be watching me do this on a board. Now, this is a cyclic form, or the hemiacetal form of fructose. I did it again. I got fructose under mine. Glucose. And I said, remember the reaction of methanol. So let's do that. And the question is, what's the organic product or the product of the following? Well, if we look at this, it's really this. And the only thing that changes is this becomes this. So if that's case, the only thing that will change is this, which is this, and it becomes this. And now, what's our triple prime? Methyl. So everything else stays the same. This bond is still there, that doesn't break, and the OH becomes O triple prime, and that's what you get. So once again, this molecule here is, in this case, the same thing, the cyclic form of glucose. And reacted with another alcohol and acid catalyst, you'll replace the hydroxyl group, just like here, with OR triple prime, which is what we did. And it's your turn. What would be the product or product for the following reaction? And take a look up there, and your turn. Thank you, Andrew. Thank you, Cristiano. So if we look at this, what do we have? The cyclic form of glucose, which is a hemiacetal, but it could have been a hemiketal. And if you react it with an alcohol, an acid catalyst, you replace this hydroxyl group, everything else stays the same, with this. And therefore, the only thing I'm going to change is that, which is this, to become to that. What's our triple prime? And propyl group. So if nothing changes other than that, I can redraw this very quickly, or maybe not that quickly. And the only thing that changes is the hydroxyl group becomes this OR, oxygen, and my R group is N-propyl. And that's how you do it. Now, why am I doing this? Well, that's how Mother Nature forms starches. And I'm going to do something on the whiteboard. Do not copy it down. Well, if you want to, I'm not going to stop you, but you don't have to, and you'll see why. And this is the cyclic form of glucose. And here it is again. Oh, let's do one more. Oh, has Dr. White lost it? No, there's a reason I'm doing these. Oops, that's not what I want. And there you have 3 glucose molecules, each one in its hemiacetal form. Now, let me remind you the reaction you just practiced. And as you saw, this hemiacetal or ketal reacts with this alcohol, acid catalyst, to form this new acetal or ketal. Now, if we look here, this right here is this carbon. And this alcohol, I can use this. And therefore, if this happens, what you get is this bonded to here. This bond right here is this bond right there. And I've now chemically linked by forming an acetal linkage to glucose molecules, 1, 2, and they're hemiacetal. Now, if we look at 2 and 3, I have this up here, and I have on the same carbon, C4, that hydroxyl group on a carbon, this alcohol. And the same thing can happen. It reacts, and it does. And you form this bond again. Right here is this one. So between 2 and 3, you also have a acetal linkage. And guess what? If I put another glucose molecule, I could add on 4, 5, 6, 7, 8, 9, 10, and you get a very long polymer of glucose, which, if I were lazy, which I can be, when n is large, like greater than 2 or larger, we call this starch. So Mother Nature takes the cyclic form of glucose, like 1, 2, 3 before I bonded them, and by this reaction, hooks them together to make all the starches in the world and cellulose. If you go out and look at a tree or anything else that's growing plant-wise, the plant cell walls are glucose held together. That reaction. Wow, is this amazing? You know, I'm an organic chemist now. I'm getting all excited. It's super amazing. And if you think about all the good things in life, like rice, potatoes, French fries, pizza, Lay's potato chips, sour cream and onion, that's all made by that reaction. The main part of that, the starch. And that's what Mother Nature uses. So what does this mean? What should you know? You should understand that if I take 50 glucose and react it with an acid catalyst, I will make starch. Oops, wrong color. And what's holding the glucose together in there? An acetal linkage. So next time you look at your favorite starch product, it's made by this reaction. Now, where does Mother Nature get the H plus? Many of the enzymes, not all, now I'm getting a little past my knowledge of expertise, but I talk to people who have worked in this, they agree with me. Many, not all of the enzymes are just very specific, special H plus acid catalyst. And that's how Mother Nature grows plants by that reaction to make the starches we get from those plants. Amazing. Now, something you should know. Sucrose, table sugar. And I'm not going to ever ask you to write this formula down. This is the acetal-ketal linkage of the cyclic form of glucose with the cyclic form of fructose. And what I would like you to know is this. And you should know when you react glucose in a cyclic form with fructose in a cyclic form with an acid catalyst, you will get sucrose, which is table sugar. You know, the white stuff you put in your, I put in my tea. Dr. White doesn't like coffee. Nothing wrong if you do, I just don't. Or if you do when you're cooking, making things that are nice and sweet, and you put in the sucrose, the table sugar, what that is a glucose and a fructose linked together by that acetal ketal linkage. Same reaction up here. And there's a reason why you've been learning these reactions, because it's now starting to fit together that Mother Nature and also organic chemists use these in their products. All right, how are we doing time-wise? Now, polysaccharides, otherwise known as starches, contain many monosaccharides bond together, and sugar chemists call glucosidic linkage. I'll never ask you what that is, but those are acetal-ketal linkages, like I just showed you, in either starch or sucrose, table sugar. Now, starch is a polysaccharide, poly meaning many, of glucose. In other words, starch is just a glucose polymer and switches off on amylose on the carbon right here. This carbon right here with the alcohol is C4. 1, 2, 3, 4. Now, sometimes the C6 alcohol can react in the same way. When it's all C4, it's linear, straight. When it's C4 and C6, this one, it can be branched. And that's two different types of starches. I will not ask that on a test ever or the final. If I look at the clock, instead of rushing through something, this is a good time. Let's take a 5-minute break and come back at 2:45, 2:46. So let's take a 5-minute break. I can get up and stretch. Now, hopefully you'll do something you're comfortable doing too, like getting up and stretching or whatever. I'll see you in 5. I'm back. Hopefully, so are you. All right, let's continue on with this exciting stuff. Now, all the stuff I've been teaching all semester is coming together. Now, we talked about, notice I say we talked about, I said you learn. We talked about how you can take glucose and link it together. And in this reaction, and here I have 1, 2, 3 glucose molecules linked together by this acetal linkage. Now, another way of showing that is here. If you look at the starch, this is using the Hawthorne projection. Now, if you notice between the two starch molecules, everybody see that on your screen right now? Thank you, Christiana. All right. And thank you, Andrew. This oxygen, the stereochemistry, you have 2 rings like this, it's below. Now, this is starch. Up here, you have cellulose, plant material, your same 2 glucose rings, except the oxygen comes from the top of one and goes underneath. And one's called alpha and the other beta, I forget. I'm not going to ask you. Now, this plays a role in hydrolysis or digestion. Now, let me remind you, what is the linkage that holds glucose together? Where did I write it? Right here. It's an acetal linkage. And an acetal-ketal linkage holds sucrose together. What does that mean? Well, a long, long time ago, test number 2, you take an acetal or ketal, react it with acid and water, what you get is you get back the aldehyde or ketone plus the alcohol you would have used to make that. And for those who wanted 2 there, I wrote it as small as I could. And that's this reaction. You break down the acetal or ketal back to the aldehyde and the alcohol you would have used to make that. Now, if you look here, what you're really breaking is this bond. So what this really means is the following. Well, I should be subtle again. When you have a starch and react it with acid and water, what do you get back? Glucose. And that's why it's the most abundant sugar in nature, because your body, my body, and animals' bodies, when they eat starch, they convert it into glucose, which your blood transports the things in your body and does things that I have no idea what it does, other than keeps me overweight. No, I should have said that. But anyways, this is what you should know. And also, if you have sucrose, you should know. You add acid and water, what do you get? Well, what's sucrose? That's glucose and fructose linked together. Therefore, if you take table sugar and react it with acid and water, you'll get back glucose plus fructose. Now, when you break it apart to get glucose, glucose is really the aldehyde and alcohol in one molecule. Whether it's the cyclic form or this form right here, glucose, don't get too dizzy while I'm coming back here. Here we have glucose. Here's our aldehyde that we started with to make our, and here's our alcohols in there, and they're just in the same molecule. So you should know, if you take starch and react it with acid and water, you'll make glucose. If you take sugar, table sugar, and react it with acid and water, you'll get glucose and fructose. You should know both of these reactions. Now the question is, where do you get this acid and water? Well, where you're sitting right now, or I'm sitting right now, where can I find acid and water real quick? In my stomach. And Mother Nature has provided the mechanism that when we consume starches, our stomach, and I believe also part of one of your intestines, some student years ago corrected me, it's not only just your stomach, but I think it's the small or large intestine, one of those two, has acid and does further breakdown. You're making glucose in your stomach. Or if you had some table sugar, you're making fructose and glucose in your stomach, mine too. But I tell you, when I was little, about 3 years old, my mother said, chew your food before you swallow or you'll choke. And guess what? I found out she was telling the truth. I did choke. And I learned that lesson the hard way. In case you're wondering, no, I didn't die. All right. Now, interesting thing. Everybody sees cellulose and starch. Something I haven't talked about, you may, thank you, Christiana, that you may have learned, you should have learned in general chemistry, is rates of reaction. How fast something is starting material is consumed, used up, how fast the reaction, a product is made. Now, it's interesting that the difference of this oxygen between the two glucose molecules has a tremendous effect on its rate of reaction. I can theorize why, but I won't. But I know for a fact, and chemists know for a fact, and carbohydrate chemists know, starch, your body can break down. Cellulose, yours can't. I'm trying to look for something. Here's a piece of paper. It's made by cellulose. It's also got some coatings on there, but that's another story. If you're starving and you eat paper, that's not going to keep you alive. If you're starving, unfortunately, and you go out in the field and eat grass or hay, that's not going to keep you alive. You need starches and other things. Why? Because starches your body can break down your stomach real fast. Cellulose has a very, very slow hydrolysis reaction rate, even with acid catalyst, which is why, now I'm going way beyond my knowledge of animal husbandry, and that is, if you've ever seen the stomach of a horse, it's huge. Not because the horse is huge, but it takes a long time for a horse to break down the grass or hay it's eating. And it needs that huge stomach to provide that time to break down the hay or starch into glucose, which keeps it alive. Same thing with cows. Now here I'm way beyond my level of expertise, animal husbandry, but I guess cows have not one, not two, not three, but four stomachs. Yep. And why do they need four stomachs? Let's check something out. That's not what I want. I've never done this. I guess I'm corrected. Everybody see, cows technically have one stomach, but it's four different compartments. They have names for them. It's different than the human. Why? That's why cows call it, but what it really means is, ooh, there's a cow. Oh, that reminds me. I'll tell you the sweet story right after I have this, I'll go through this. It needs these four areas of their stomach to have a very long reaction time of when they break down grass, or hay that they're eating that the farmer gives them, or grain. Grain, you could probably, they break down quicker, but a lot of cows obviously are fed, and now I'm way beyond my level of expertise, animal husbandry, either out in the field, they're eating grass, or the farmer gives them hay. Now, cute story, when my younger sister, when we were about, she was about 3 or 4, my parents, we did a road trip. Well, the only one I think we really did, major one summer. We went from Chicago through different states up to Niagara Falls, and then back again, a different route. And we were in the middle of somewhere in Indiana or Michigan. My sister saw this big field with cows, and we still kid her about it, and we're not young chickens anymore. But anyways, she'd say, "Look at the cows out there," and we'd love that. We still get a kick about remembering that. But anyways, that's because of the difference in hydrolysis. So starches you and I can break down easily, cellulose don't. Now, one of the things that I thought about during our break, Dr. White, that I should have done earlier that I'll do right now. Leaving my class, there's some important things you should know. Hint, and you should know the following. How do you describe with words and a general chemical reaction what happens in your body when you eat something with a fat or oil? So how do you describe with words and a general reaction what happens when you eat a fat or oil? Well, what's the functional group in a fat or oil? That's an ester. And when you eat it, it goes in your stomach, it's acid hydrolysis. Acid hydrolysis, I could have put down acidic too, but of an ester. And for test 3, you learn ester, acid, and water gives back the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. So you should know when you eat a fat or oil or food that contains that, how to describe with words and a general reaction what happens in your stomach. And the answer for fat or oil is acid hydrolysis of an ester. And the general reaction is ester, acid and water, carboxylic acid, you get back in the alcohol you would have used to make that ester. And now you should be able to describe with words and a general reaction what happens when you eat a carbohydrate. And this you should know. What's the functional group that holds glucose together in a carbohydrate? And that's an acetal. So this is acid hydrolysis of an acetal. And you learn for test number 2, take an acetal or ketal, and react it with acid and water. Keep your eye on a carbon with 2 oxygens. That becomes this carbon. What's attached to it, R prime or hydrogen, and R double prime. And you get back the alcohol you would have used to make that acetal or ketal. And for those who want, you could put a 2 there. I wouldn't. You don't have to. And therefore, whenever you eat a carbohydrate, later today, if you have a piece of bread, remember, chew your food before you swallow it or you'll choke. I learned that the hard way, as I mentioned earlier. After you swallow it, when it goes in your stomach, there's acid and water. So it's acid hydrolysis and the functional group between the glucose of an acetal. And the general reaction is acetal or ketal, acid and water, gives you back the aldehyde plus the alcohol you would have used to make that acetal or ketal. This you should know for test 4 and the final, which coming up in a couple of weeks. Where did this semester go? I guess time flies when you're having fun with organic chemistry and Dr. White. It did for me so far. All right. Now, cellulose is this molecule, and that's what makes up plant walls. Now, I'm way beyond my level of expertise, but I do know that. And if you look at cellulose, what do you see in that molecule? Lots of hydroxyl groups on carbons, alcohols. So let's look at an interesting molecule. Now, I'm going to pull up a product, and in no way am I telling you should buy it or use it for what it's. Now, there's a product made by a company called KY, and it's a personal lubricant for certain personal things you can do on whatever. But anyways, if you look at the ingredients, water, I know what that is. Glycerin, I know what that is. Hydroxyethyl cellulose. Let's take a look at this. What the heck is hydroxyethyl cellulose? Everybody see hydroxyethyl cellulose on your screen right now? Thank you, Christiana and Andrew. All right, if you look over at the right, they have, notice R on this ring can be H or CH2, CH2OH. And when it's mostly CH2, CH2OH, that's hydroxyethyl cellulose. Well, how is it made? Well, good question. Long time ago, for test number 2, if you take ethylene oxide and react it with an alcohol, you'll make this ether alcohol. Oxygen with CH2, CH2OH. Well, guess what? Companies, which you can buy very inexpensively, everybody see the structure of cellulose? These hydroxyl groups you see here, these 3, can be ethoxylated to make hydroxyethyl cellulose. This molecule. And this is a very good thickening agent to make gels. It says here, right in print. And it's derived by reacting cellulose with ethylene oxide. Now, notice it's widely used in a lot of stuff, including cosmetics. And I showed you one, and that was KY jelly. There's some other things, but this is a thickening agent. If you look at a lot of things, you can see that. Now, it's also used in drilling for drilling muds as an additive to make it thicker. And how does it do that? Well, it hydrogen bonds to water. Just like you saw with the Elmer's glue and boric acid, this being a monster long molecule, N is huge. When you have R as CH2OH, CH2, CH2OH, you can now hydrogen bond to a lot of water and other things and thicken things up. And like I said, one of the main ingredients is personal lubricants. And it's also, for forming big bubbles. I didn't know that. What's slime? Oh, okay. I've always seen them use Elmer's glue and boric acid, but there are other things that will thicken it. But, well, I've got to get my hands on some and see if it does that. And that's why we're learning things like this. Let's do one more while we're here. Oh, I used to have a nice picture. They changed it. Ooh, hold on. There we go. Everybody see the pictures of like this clear cello caramel wrappers or taffy wrapper? All right, that plastic, which is called cellophane, is made from cellulose. And it's that crinkly stuff you get around candy like they showed here. And things don't stick to it that well, candy-wise, obviously. And how is it made? and it's chemistry I've never done. Everybody say if you take cellulose and react it with sodium hydroxide and carbon disulfide, I don't even know the name of this functional group. See, I don't know everything about organic. This is the structure of cellophane. And it's that crinkly clear stuff. That's a polymer that they can make sheets out of and cut little pieces and wrap candy about it. Now, something I haven't talked about is if you put a nitro group, you can take alcohols and nitrate it, and I stayed away from that on purpose, like a nitroglycerin. But anyways, cellulose could be and has been nitrated. Now, this is used to make gun cotton, but originally, and everybody see the molecule of nitrocellulose from Wikipedia on your screen? Thank you, Christiana. This material, this polymer, they found back in the 1900s, made a nice clear film polymer. And they used that to make and record motion pictures, which has the, now they're digital, but back then it was on film. Well, it turned out nitro compounds like that are not stable. Nitroglycerin, give you an idea. And about 1950s, 1960s, and 70s, some of the old movies, great movies from the 1900s, 1910s, started catching fire in the vaults they were held. And that's because they were on an unstable plastic, nitrocellulose. And who's the director who did Raiders of the Lost Ark and all that? I have a mental block. Well, I've got Google. Steven Spielberg. I couldn't think of his name. Who's got a lot of money because he's been very successful. I love his movies. But anyways, he got together some other people and they started taking those films before they disappeared, destroyed, and recorded them on more stable media and eventually digital media too, which is why, but originally that came from taking cellulose, the alcohols there, and making nitrocellulose. So once you've learned, now you've learned them, think about that. The general reactions I have taught you this semester, they are used to make products in our everyday life. Along our road, I've shown you some of those. Now let's go back and do a little review, because review is good for your grade, which makes Dr. White happy. All right, remember, if you take some glucose and react it with acid, you'll make starch. If you take glucose and fructose, react it with acid, you make table sugar. Now, you can go the reverse way by this reaction. Both of these, starch and sucrose, are essentially hemiacetal or hemiketal linkages. If you add acid and water, like in your stomach, you break them apart again to what you started with. In the case of starch, if you take that acid and water, you'll get back glucose. That's what happens in your stomach to make the glucose that's in your blood to keep you alive. How that does that, I have no idea, but I know it breaks it down to that. Now, sucrose, you should know, you have sucrose, table sugar, acid and water. You get back to glucose and fructose you use to make that. Which reminds me of an interesting thing I should mention. This is my own personal opinion, so you know it is, but I believe it's a good personal opinion. A number of years ago, there are these mothers groups that were going around saying all this fructose in our kids' diet from high fructose corn syrup to make products sweet, like they're putting it into pop, they still do somewhat, or into baby food, into cereal. That's bad for the health of our children. The fructose is causing all sorts of maladies in our kids, autism and all that. Now that part, the fructose causing that, I don't buy. I think personally, and I know from personal experience, you got to watch out. Eating too many calories and stuff that's high in fructose, is a lot of calories, is bad for your health. You'll be overweight, and that's not good. But what the food companies did was, oh, we hear your pain. And guess what? We're going to cut back on the fructose in our products. So what do? Replace some of the fructose with sucrose. And the mothers group, all right, we're not as mad. Well, no. Why? Because when you eat sucrose, you're still making fructose. Maybe not as much, but you're still causing that to be formed in your body. And that's why I don't buy the fructose is causing these problems in children. I would say it's just a high calorie content. Unfortunately, I know about that. And not that I've had autism or things like that. But I don't believe it's the fructose, because mankind has been consuming sucrose since the late 1800s when it was available to the common person. Before, sugar was very limited to only the rich, but now anybody in our society in the United States, you can go out and buy at many places for larger pound bags of table sugar. And that's just my personal opinion. Now, let's go through this again. You should know how to describe leaving my class with words and a general reaction. First of all, what happens in your stomach when you eat something with a fat or oil in it? And the way you describe it with the words, the key functional group in a fat or oil is an ester. And that's in your stomach, acid and water, and we call that hydrolysis, acid hydrolysis of an ester. And the general reaction you learn for test number 3, ester, acid, and water, you get back the carboxylic acid and the alcohol you should have used, you would have used to make that ester. You should know this for test 4. See, it even says that. Hint, know this. So if I ask on a test 5 points or 4 points, describe with words or a general reaction what happens when you eat a fat or oil, that would be acid hydrolysis of an ester. If I ask, and the general reaction is ester, acid, and water, you get back to carboxylic acid plus the alcohol you would have used to make that ester. Next, if I ask on a test, like test 4 or the final, describe with words and a general reaction what happens in your stomach when you eat a carbohydrate. And what functional group is in a carbohydrate? Acetal. And it's acid hydrolysis of an acetal. And the general reaction is this one. Acetal, ketal, acid and water, get back the aldehyde or the ketone plus the alcohol you would have used to make that acetal or ketal. And carbohydrates, what you get back is glucose, which is the aldehyde and the alcohol hooked together. And if you're doing sucrose, you also get fructose. Now, while I still have some time, and I do, something I'd like to make you remember. Boy, am I being subtle today? Uh-oh. Hold on. It's my computer's burping at me time. Nope. Sorry about that. All right, let me just check. Everybody see my whiteboard? Hint, know this? Uh-oh. Oh, thank you, Christiana. Thank you, Andrew. All right, now it works. And the question is, how does soap work? And hint, you should know this. You should know the structure of soap. Non-polar tail and a polar head. All soaps, whether it's liquid or solid bar soap or your laundry detergent. Now, the most important part of the puzzle, how does soap work? And go to a real large font. Like dissolves like. And like dissolves like, things that are polar are soluble in polar things. Things that are nonpolar are soluble in nonpolar things. If you mix the two together, polar and nonpolar, they're not soluble. So because of like dissolves like, water and dirt won't get you clean with water. Let's take a big little magnify a tiny piece of dirt. This is nonpolar. The soap has a nonpolar tail and a polar head. And because of like dissolves like, the polar head wants to stay away from the dirt, but the polar tail wants to get near the dirt. Nonpolar tail wants to get near the dirt. I'm just going to show 4 molecules, even though there's lots and lots more. And it forms something you should know, a micelle. And the water looks at the micelle and says, oh, micelle. And all it sees are the polar heads all around the dirt. Micelle, you're polar, I'm polar. Let's go down the drain together. And they do. So you should know, how does soap work? You should know that soap, the general structure, non-polar tail, polar head. The most important thing, how soap works, does soap work, is like dissolves like. And like dissolves like, as you learned from last week's lab, is things that are polar are soluble in polar things, things that are nonpolar are soluble in nonpolar things. You mix together, two together, not going to be soluble. So dirt and water won't get dirt clean, but when you use the soap and you go like this with the soap and water, what you're forming is micelles. And then when you rinse off your hands, guess what? Water sees the micelle, says, oh, like dissolves like, micelle, and only sees the outer polar heads of the micelle. You're polar, I'm polar. Let's go down the drain together. And they do. Not to get personal, but when I took my morning shower this morning and lathering up, guess what? I was probably the only one around here who was thinking, oh, I'm making micelles to get me clean. Now, I think I might have mentioned this before. There's a product a number of years ago, students in my Chem 170, women, said, have you heard of this thing, micellar water? Right after I taught about how soap works. I said, no. So I looked it up, and I was told by my students it works real good, especially getting makeup off your face. As you can tell, I forgot to wear any, oh, don't look. Anyways, it has aqua water, ethylene glycol, glycerin, and various different things. It doesn't have any micelles. It forms micelles on your skin when you use it. And that's how you get your face clean or whatever you use it for. I assume it's mainly the face, those are used for, that product. And you're just forming micelles. But someone very clever who knew how soap works and who was a good marketing person came up with the idea, let's call it micellar water. Because most people who buy those products have no idea of the organic chemistry or how things work. Guess what? You are now learning that stuff and you have that knowledge. As my father always reminded me, nobody can ever take knowledge away from you. Nobody can ever take an education away from you. And he was right. And thank goodness I did get my education in chemistry. And with that, I think I'm going to end a little early, and we're done for today. On Wednesday, I will go through the fats and oils problem set. On Wednesday, I will go through the lab. This is an exciting lab, one I created. I created them all. But anyways, this one's my favorite. I wish we were face-to-face. And you'll see, oh, this is a lab you can do at home on your own, not for the lab, but just to have fun, and it is. But with that, I'm going to say, don't forget, keep on studying. You're doing good, and gehen gesund, go in health. Oh, and I forgot to tell you, last Friday, I got my third booster, the one that's for the COVID that's running around right now. Not too bad, but still dangerous out there. So get your booster. With that, I'll say gehen gesund. That's Yiddish for go in health. And goodbye now. I'll see you on Wednesday.